You know how you can look at a topographical map and just instantly understand an entire mountain range without ever having to climb it? Well, today we're going to use that exact same idea to map something that's completely invisible, the electric field. It might sound kind of complicated, but trust me, by the end of this you'll see how physicists use this really clever trick to understand the hidden forces that basically power our world.
So let's just start with the main problem, right? Electric fields are literally everywhere, pushing and pulling on things, but we can't see them. So how in the world do you draw a map of a force that's invisible? It's a great question, and the answer is actually surprisingly simple and pretty elegant.
The key to the whole thing is an analogy that most of us are already familiar with, a topographical map. I mean, think about it. This map takes a super complex, three-dimensional landscape, with hills and valleys, and it just flattens it onto a 2D page. It uses those simple little contour lines to show you the altitude. It's a genius way to visualize a landscape.
And that is exactly what we're going to do here. We're going to imagine that an electric field is like an invisible landscape of, let's say, electrical hills created by positive charges and valleys created by negative ones. We can map this invisible terrain using the exact same logic as that mountain map.
Okay, so if we're going to make an electrical map, the very first thing we need is a way to measure the altitude at any given spot. In our invisible landscape, that altitude has a special name, electric potential.
So electric potential, which you probably know better as voltage, is really just a number assigned to a point in space. That's it. Physicists call this a scalar quantity. It tells you the potential energy at that spot. Kind of like saying your altitude is 500 meters. It has a value but no direction. And that simplicity? Well, that's its superpower.
And here's why that superpower is so important. The electric field itself, well, it's a vector. That means at every single point in space it has both a strength and a direction. If you want to find the total field from a bunch of charges, you have to do all this complicated vector addition, worrying about angles and components. It's a mess. But electric potential, it's just a number. You just add them up. It is so much easier to calculate the altitude everywhere than it is to directly calculate the complex slope of the field.
Okay, so if potential is the altitude, then what is the electric field? Well, let's go back to our mountain map. Once you know all the altitudes, you can easily see where the steepest parts are, right? The electric field is exactly that. It always points in the direction of the steepest downhill path in our invisible landscape. And the source material puts it perfectly here. The electric field at any point simply shows you which way the potential, our altitude, is dropping the fastest. So if you were to place a positive little test charge in this landscape, this is the direction it would instantly start to roll. It's the path of least resistance, downhill. Let's really picture this. A positive charge acts like a peak or a hill in our landscape. It creates a spot of really high potential. So the electric field lines, which we always draw as arrows pointing away from a positive charge, are just showing the direction a ball would roll if you place it on the side of that peak. They're literally mapping out the steepest path downhill. And in physics, this whole map analogy gets boiled down into one beautiful, concise equation. Now, don't get thrown by that upside-down triangle. It's just a math symbol for gradient, which is really just a fancy word for slope. So all this equation is saying is exactly what we've been talking about. The field, that's E, is just the slope of the potential, that's V.
But hold on, what about that little negative sign? That is actually the most important part of the whole equation. Why is it there? Well, because things roll downhill, not uphill. That negative sign is the math way of saying the electric field always points from a higher potential to a lower potential. It points in the direction of decreasing altitude, which, of course, is exactly what our intuition tells us should happen.
Okay, let's add one more feature to our map. You know how every good topographical map has those contour lines that connect all the points of the same altitude? Well, our electrical map has those too. We just call them equipotential surfaces.
An equipotential surface is, well, it's exactly what it sounds like. It's a surface where the potential, the voltage, is the same everywhere. If you were to move a charge anywhere along one of these lines, it'd be like taking a walk on a perfectly level path around the side of a mountain. It takes zero work because you're not going uphill or downhill.
Now, these contour lines have some really important rules. First, they are always perpendicular to the electric field lines. And that makes perfect sense, doesn't it? The steepest downhill path has to be at a right angle to the totally level path. For a single little point charge, these surfaces are perfect spheres. And here's a super useful fact to remember. The entire surface of any conductor, like a piece of metal, is always an equipotential surface.
So you might be thinking, Why go through all this trouble? Why create this imaginary landscape with hills and contour lines? Well, because it gives physicists an incredibly powerful shortcut for solving some really, really difficult problems.
This is the payoff. This is the whole point. Instead of trying to calculate that complicated vector field directly, you can use this simple three-step method. Step 1, you calculate the easy scalar potential. You're just adding up numbers to map the altitude everywhere. Step 2, you look at your map, and at any point you care about, you find the direction of the steepest downhill slope. And step 3, that slope is the electric field vector you were looking for. It's a brilliant strategy. You find the hard answer by first calculating the easy one.
So we've pretty much established that our invisible landscape shows the path a positive charge will take. It's like a ball rolling downhill, from high potential to low. But that leaves us with one last little thought to ponder. What would a negative charge, like an electron, do in this exact same landscape? We'll leave you with that to think about. Thanks for joining this explainer.